Welcome! In this video, we'll be diving into the world of AP Precalculus Topic 3.7, Sinusoidal Function Modeling. By the end of our session, you will be able to construct sinusoidal function models to describe periodic phenomena. In other words, you'll learn how to take real-world data that follows a repeating pattern and turn it into a mathematical equation. Why is this important? Because a huge number of natural processes repeat in cycles. Think of the phases of the moon, the tides, the temperature outside changing from day to night, or even your own heartbeat. These are all examples of periodic phenomena, and we can use sinusoidal functions, sine and cosine, to create powerful mathematical models that describe them. In this video, we'll break down the key components of a sinusoidal function and learn how to extract those components directly from a set of data. Let's get started. First, let's refresh our memory on the anatomy of a sinusoidal function. The general form of these equations might look a little intimidating at first glance, but we'll see that it's made up of four key pieces. We often write the general form as y equals a times the sine of b times the quantity x minus c plus d. Similarly, we could use cosine instead of sine, so y equals a times the cosine of b times the quantity x minus c plus d. Both represent sinusoidal waves, just shifted horizontally relative to each other. Let's break down what each of these parameters, a, b, c, and d, means for the graph of our function. First, we have a, which is the amplitude. The amplitude determines how tall the wave is. It's the maximum displacement from the midline. Next is b. B affects the horizontal compression, which in turn determines the period. The period, or t, is the length of one complete cycle of the wave. Then there's c, the phase shift. This tells us the horizontal displacement, or how much the wave has been shifted to the left or right. And finally, d is the vertical shift. This value moves the entire wave up or down, and it also defines the midline, which is the horizontal line that passes through the center of the wave's oscillations. So, we have amplitude, period, phase shift, and vertical shift. Our goal in modeling is to figure out what numbers to plug in for a, b, c, and d to make our equation match the data. Let's work through an example to see how to find these parameters. Imagine we're tracking the temperature in a city over a day, and we've gathered the following data. We have the hour of the day, with 0 being midnight, and the corresponding temperature in Fahrenheit. We'll assume the temperature follows a sinusoidal pattern. Our task is to find the function t of t that models this data. The first step is to find the vertical shift d and the amplitude a. We can get these directly from the maximum and minimum values in our dataset. Let's look at our data. The maximum temperature we see is 86 degrees, and the minimum temperature is 50 degrees. We'll call these Tmax and Tmin. So, our maximum is 86, and our minimum is 50. The vertical shift, d, represents the midline of our function. It's the average of the maximum and minimum values. We can find d using the formula. D equals the quantity t underscore max plus t underscore min, all divided by 2. This formula calculates the average, which is the exact center between the highest and lowest points. Plugging in our values, we get d equals 50 plus 86 divided by 2, which equals 136 divided by 2, or 68. This means the midline for our temperature function is y equals 68. Now for the amplitude, a. The amplitude is the distance from the midline to the maximum or minimum. It's how much the function swings up or down from the average. We find a using the formula a equals the quantity Tmax minus Tmin, all divided by 2. This gives us half the total distance between the highest and lowest points. Substituting our values, a equals 86 minus 50, divided by 2, which equals 36 divided by 2, or 18. So, our amplitude is 18. This means our temperature will fluctuate 18 degrees above and below the average of 68 degrees. Great! We have d equals 68 and a equals 18. Now, let's move on to the next two parameters, the period and the phase shift. The period t is the length of one full cycle. We can find this by looking at the input value interval between consecutive maxima or consecutive minima. Looking at our data, the temperature is 50 degrees at time t equals 0, and again at time t equals 24. Since 50 degrees was our minimum, this indicates a full cycle. The period is 24 minus 0, which is 24. So, our period t is 24 hours. The temperature cycle repeats every 24 hours. Now that we have the period, we can find b. The parameter b is related to the period by the formula t equals 2 pi divided by b. We need to rearrange this to solve for b, so b equals 2 pi divided by t. Plugging in our period of 24, we get b equals 2 pi divided by 24, which simplifies to pi over 12. So b equals pi over 12. This value of b compresses our sine wave horizontally so that one cycle fits into 24 units. Okay, we're almost there. We have a, b, and d. The last parameter we need is the phase shift, c. The phase shift, c, tells us the horizontal starting point of our sine or cosine function. The choice between sine and cosine affects what the starting point means. A standard cosine function starts at its maximum value at x equals 0. A standard sine function starts at its midline and is increasing at x equals 0. Let's look at our data again. At t equals 0, the temperature is 50. What is 50 in relation to our midline of 68 and amplitude of 18? It's our minimum value. Since our data starts at its minimum, we can model this with a reflected cosine function, or y equals dash cosine. A reflected cosine function starts at its minimum at x equals 0. Because our data's starting point perfectly matches the reflected cosine function's starting point, we don't need to shift it horizontally. Therefore, our phase shift, c, is 0. If our data had started somewhere else, like at the maximum temperature of 86, we would use a cosine model, and the phase shift c would also be 0. If it had started at the midline and was going up, we'd use a sine model, and c would be 0. We'll see how to find c when it's not 0 in our next example. Okay, let's put it all together to write our model. We've found all the pieces. We determined that the amplitude a is 18, the parameter b is pi over 12, the phase shift c is 0, and the vertical shift d is 68. Because our data started at a minimum, we chose to use a reflected cosine function, which is a regular cosine function multiplied by -1. So our general form becomes t of t equals -a times cosine of b times t plus d. Now we substitute our values. T of t equals -18 times cosine of pi over 12 times t, plus 68. This is our final sinusoidal model for the temperature data. With this function, we can now make predictions. For example, what would the temperature be at t equals 20, or 8 p.m.? We plug 20 into our function. That's -18 times cosine of pi over 12 times 20, plus 68. Pi over 12 times 20 simplifies to 5 pi over 3. The cosine of 5 pi over 3 is 1/2, so we have -18 times 1/2 plus 68, which is -9 plus 68, or 59 degrees Fahrenheit. This shows the practical power of these models. From just a few data points, we can predict values we didn't measure. Let's try another example where we'll encounter a phase shift. Suppose we have the following data for the position of a weight on a spring, where t is time in seconds and y is position in centimeters. Here's our data. The maximum position is at t equals 2, and the minimum is at t equals 6. As before, we start by finding the vertical shift d and the amplitude a from the max and min. The maximum position is 5, and the minimum position is -1. d equals 5 plus -1 divided by 2, which is 4 divided by 2, or 2. So the midline is y equals 2. A equals 5 minus -1 divided by 2, which is 6 divided by 2, or 3. The amplitude is 3. Next, let's find the period. A full cycle is the time between a maximum and the next maximum, or a minimum and the next minimum. We're given a maximum at t equals 2 and a minimum at t equals 6. This is half a cycle. The time it takes to go from a max to a min is the period divided by 2. So, t equals 6 minus 2, which is 4 seconds. Since 4 seconds is half a period, the full period t must be 8 seconds. To find b, we use b equals 2 pi divided by the period, 8. This gives us pi over 4. So, b equals pi over 4. Now for the phase shift, c. In our previous example, the data at t equals 0 matched a standard sine or cosine function. This time, it does not. At t equals 0, we have no information. However, we do know that the maximum occurs at t equals 2. The cosine function normally has its maximum at t equals 0. Therefore, our phase shift c is 2. This value of c shifts our entire cosine curve 2 units to the right, aligning its maximum with our data point. Let's assemble our model. We have a equals 3, b equals pi over 4, c equals 2, and d equals 2. Using a cosine model, we get y equals 3 times cosine of pi over 4 times the quantity t minus 2 plus 2. Let's check this against our data. At t equals 2, the model should give 5. Plugging in 2, we get pi over 4 times 0 inside the parentheses, which is 0. Cosine of 0 is 1. So we have 3 times 1 plus 2, which equals 5. It matches. And at t equals 6, it should give minus 1. Plugging in 6, we get pi over 4 times 4, which is pi. Cosine of pi is minus 1. So we have 3 times minus 1 plus 2, which is minus 3 plus 2, or minus 1. It also matches. This confirms our model is correct for the given data points. So far, we've focused on finding the parameters by hand. But what about more complex noisy data? That's where technology comes in. You can use your graphing calculator or online tools to perform a sinusoidal regression. Sinusoidal regression is a statistical method that finds the best fit sinusoidal curve for a set of data. This means it might not hit every single data point exactly, but it will be the curve that minimizes the overall distance from the points. Here's the general process for most graphing calculators, like a TI-84. First, you enter your data into two lists. Second, you go to the Stat key, then to the Calc menu, and select option C, which is SynReg. The calculator will then compute the values for A, B, C, and D for you. Once you have these values, you can write the function and use it for predictions. Technology is an incredibly powerful tool for modeling real-world data, especially when it's not as clean as the examples we've seen. Finally, there's a crucial point to remember about all mathematical models. They have limits. Sinusoidal functions are periodic, meaning they repeat forever. For the temperature function, our model would predict that the temperature is 50 at midnight every single day for the rest of time. Is that realistic? Of course not. The model is only useful and accurate within a specific realistic domain. For our temperature example, it's probably only valid for the 24-hour cycle we measured, or perhaps a few cycles. It cannot predict the temperature a year from now. This idea of a contextual domain is essential for interpreting the results of any model. Always ask yourself if your prediction makes sense in the real-world context. In conclusion, we've learned how to construct sinusoidal models from data by identifying its maximum and minimum values, its period, and its phase shift. We've also discussed the role of technology and the importance of contextual interpretation. You are now equipped to tackle periodic phenomena with the powerful tools of sinusoidal functions. Great job!